Alright, so we're back again. Let's see, today we're working on the Investigating Bisectors and Triangles Part 4 packet. Specifically, we're going to look at the Euler line, that last problem on the back page. Alright, it says that the Euler line includes both the circumcenter, the centroid, and the orthocenter. So we need to first think about it. Circumcenter is the intersection of the perpendicular bisectors. So if we do the perpendicular bisectors of all three segments and see where they cross, then that'll give us that circumcenter. So we need a perpendicular bisector for all three segments. Alright, so let's put a point there, and that point D is the circumcenter. So we'll go ahead and label that off here to the side so that we can remember it. Alright, now for the time being, let's hide those lines. We've got the point that we need. There's the first one. Now we need the centroid. The centroid is the intersection of the medians, and remember, a median connects a vertex to the middle of the opposite segment. So we need the midpoint of each of these segments. And then we'll draw some segments in there as medians. Alright, so from the vertex to the midpoint of the opposite side. Vertex, midpoint of the opposite side, and the last one as well. So we'll go ahead and put a point there where they intersect. And that point, as we said before, the point of concurrency of the medians is the centroid, and that's H. Alright, so like we did before, let's hide those median segments for a bit so that we can keep just the point. The other one that we need is the orthocenter, and remember, an orthocenter occurs where the three altitudes intersect. An altitude starts at a vertex and goes perpendicular to the opposite side. So we need a perpendicular line that goes from vertex A down to its opposite segment BC. And remember, that's going to create a right angle right here. Do the same thing from B, perpendicular to the opposite side. And lastly, from C, perpendicular to the opposite side. We can see that point of concurrency there then that we're going to name I. And that is our orthocenter. Alright, so there's those. Let's go ahead and turn these off momentarily. Now notice that those 3 points, D, H, and I, the circumcenter, the centroid, and the orthocenter, are collinear as Euler's line says that they should be. So let's go ahead and take our line here, and we'll create a line through all 3 points. And we'll go ahead and change the color of that line so that we can kind of keep track of it a bit. On your paper, you're asked to draw that line in some sort of color so that it shows up well. And as we move the triangle around, then these vertices of the original triangle, we can see that here, when the triangle is obtuse, the orthocenter is outside, like we expect it to be for altitudes, and the circumcenter is outside, like we would expect to see for the perpendicular bisectors. We can move it around some more and kind of see that they're all going to stay right on that Euler line. And here we can see where the circumcenter ends up the midpoint of the hypotenuse, and the orthocenter ends up at the vertex of the right angle, like it should for a right triangle. So ultimately those 3 points then are collinear, and that is the Euler line. Now it goes a little further to discuss something called the 9-point circle. The 9-point circle kind of has different varieties, different names, depending on who you think brought it up and various other details. The 9-point circle is a variation of a 6-point circle and a 12-point circle and so on. And each of these circles contains specific points from the triangle. For example, the 9-point circle that we're looking at says it should contain the midpoint of each side, the point on the side that is one end of an altitude, and the midpoints of the segments that connect the vertex to the orthocenter. So let's look at how that looks. Alright, the point on the Euler line, that is the midpoint of the segment connecting the orthocenter and circumcenter. Remember, we're looking at I and D. So the midpoint of I and D, let's go ahead and do that. We between D and I, and that's named that J. So that's our new midpoint. That is the center of the 9-point circle. So I'm going to grab this circle tool, and I know J has to be the circle's center. It says that it's going to pass through the midpoint of each side of the triangle. So here, if I extend it out to F, we can see it hits F, E, and G, those 3 midpoints, like it should. It says it should hit the end of the altitude that is on the side of the triangle. Now notice that means here, remember, an altitude from B will be perpendicular to the opposite side. So let's turn those altitudes back on for just a second. Whoops, that's a perpendicular bisector. That's not what I want. There we go. And notice, like the one we were just talking about from B, the altitude there intersects where that circle's at. So that's another point on that circle. And if I take each of those altitudes and trace it over to where the opposite side occurs, you can see that's where the circle and the line will both meet. And here again on the last one from A. So let's go ahead and hide those lines again for a minute so you can see what that circle actually looks like. So these points then, notice we have 6 of them right now. 1, 2, 3, 4, 5, 6 are 6 of the 9 points on the 9-point circle. Now it says the others are the midpoints of the segments connecting each vertex to the orthocenter. So if I'm looking at B, the vertex, to the orthocenter I, if I find the midpoint between those 2 points, it will be on the circle. So let's try the midpoint of a vertex to the orthocenter. And see, there's where N appears on that circle. And it says that should occur from each vertex to the orthocenter. So here again, from A to I, O ends up on the circle. And last one, from the vertex C to I, we end up with another point on the circle. And as we move those vertices around, then we can see that those points lie on the circle at all times. Sometimes they become kind of concurrent points when the triangle is one of our special types. But ultimately, we end up with 9 distinct points on that circle, most of which are direct points from the lines that we've drawn in, be it the midpoint, which is used by both the perpendicular bisector and the medians, or the foot of an altitude, that perpendicular line from a vertex to the opposite side. And some of these other ones, like this one, that's not necessarily a segment that we've drawn, but it's still a point on the circle itself. So that takes care of the Euler line, which we see here in blue, and the 9-point circle. And on your paper, you only need to construct the Euler line. Don't worry about doing the circle.